every password you've ever set, every Git commit, every file you've downloaded and checked. They all pass through one function, and it turns data of any size into the same short fingerprint. Change a single letter of the input and the whole fingerprint changes. By the end of this, you'll have built that function from scratch, and it'll match the real one exactly. A hash is a fingerprint for data. Feed it anything, a single word or a whole movie, and you always get back the same 256 bits. The same input always gives the same output. But there's no way to run it backwards, and the tiniest change scrambles the result completely. That combination is what makes it useful. You rely on this constantly without seeing it. Websites store a hash of your password, never the password itself. Git names every commit by its hash. When you verify a download, you're comparing hashes. Trust on the internet leans on one idea, that a fingerprint is easy to compute and practically impossible to fake. The algorithm starts with a pile of constants that look random. They aren't. They are the fractional parts of the square roots and cube roots of the first prime numbers. We compute them ourselves, so there's nothing hidden, no secret seed. Just arithmetic. Anyone can check. The function works on fixed size blocks, so first we pad. We add a single 1 bit, then zeros, and finally the original length written at the very end. That length is the clever part. It makes two different messages that happen to look alike after padding impossible to confuse. Each block gives us 16 words. We stretch those into 64 by mixing earlier words together, shifting and rotating them. The point is to take every bit of your input and start smearing it across the whole block, so nothing stays in one place. Now, the engine, and it's made of tiny pieces. Rotate the bits of a word, exclusive or a few rotations together. Pick bits from one word or another depending on a third. None of these are clever on their own. The strength comes from stacking them over and over. This is the heart of it. 8 working variables and 64 rounds. Each round folds in one scheduled word and one of those prime constants, then shuffles everything down by one. Round after round, any pattern in your data gets beaten flat into noise. What should actually run? These are the 8 variables, 1 per row, and we step through all 64 rounds. Look how much changes at every single step. By the end, there's no trace left of the orderly numbers we started with. After the rounds, we add the result back into a running total and move on to the next block. That carryover chains the blocks together, so the final fingerprint depends on every byte that came before it. Miss a single bit anywhere, and the ending changes. Here's the property that matters most. Take a sentence and hash it. Now change one letter and hash it again. About half of the output bits flip. There's no smooth relationship between the input and the output, and that's exactly why you can't work backwards from a fingerprint to the thing it came from. That's the whole function. To prove it's real, not just plausible, we hash a file with our code and with the system's own tool, the one built into your computer. The two fingerprints are identical, character for character. You didn't call a hashing library. You became one.